Oh, it's filming. Say hi. Hi, Jenna. Jenna's not here, I think. So, okay. See if it's aimed. Maybe we'll move this closer to
At the water bucket?
Oh, Brian, will you go back? Hold on. I'm going to send Joseph because you know where my classroom is. My Sunday school classroom, the middle school girls' room, there's a bag full of safety goggles that we'll need on the bookshelf. Thank you. Okay. So, are we good? Can it see me? And it might have to see the board eventually. Yes. Yes. Yeah, go across the hall over there. There's a little kid bathroom back there with like the tiny... Not ideal. The atmosphere is a mass of air surrounding a planet, right? So if you picture the Earth as like a soccer ball kind of size, then how big do you think the atmosphere around the Earth would stick up off of it? Would it be like... you watched the video? There we go. Okay, so the atmosphere of the Earth, compared to the size of the Earth, is quite thin. Just a couple of, millimeters? My memory is terrible. But for us, it seems quite immense. It goes up, many hundreds of kilometers from the surface of the Earth. The gravity of the Earth holds the atmosphere around the Earth. And the atmosphere exerts a large amount of pressure on us right now. So if you think, has anyone ever, thank you, has anyone ever dived to the bottom of a deep pool, like a 12-foot pool? What do you experience when you're like deep underwater? Your ears yeah, because your little eardrums are kind of a place where your body can experience pressure more than other places, and like the crushing depth of water can really make your ears hurt, and the cause of that pressure on your ears is that weight of the column of water that's above you pressing down on you. And water is something that we can feel and experience and understand, but because it's so normal and because our body exerts pressure back out against the atmosphere of air, we don't really experience air pressure on a day-to-day basis. But just like when you're 12 feet underwater, that column of water is on top of you. There's a column of air straight up from the top of your head all the way up to space, and it's pressing down on you right now. And, of course, we've already learned that air is composed of gases that are matter, and it has mass, and it takes up space. And if you think of that column of air sitting right on top of your head, pressing down on you, it exerts 14.7 pounds of pressure per square inch of you. So, think an inch, right? A square inch, 14.7 pounds per square inch, pressing down on you. There's an enormous, massive column of air pressing down on you that goes all the way up to space. Okay, and you don't see it, and you don't really experience it, but it's there.
Why do we feel more pressure deep underwater than we would, let's say, in the air?
Well, because the mass of water, water is a liquid, so it's much denser than a gas, and so the mass of it is there, and it's just more than what we normally experience. Plus, we can feel the water. We don't, notice the air. So, water definitely way denser, though, than a gas. So that would be mainly the thing. The atmospheric pressure that we experience changes with the weather. So it's not always going to be that 14.7 pounds per square inch. When a low pressure system comes in, that will be it'll decrease a little, and when there's a high pressure system, it'll increase a little. And you guys will be experts at that by the end of module 6 or 7. So don't worry. But it can change. It doesn't stay the same, right? Air masses come and go, and the weather changes, and our atmospheric pressure changes. Atmospheric pressure also changes if you go up in altitude. Here, we're pretty well at sea level. We're not very far from sea level here. We live close to the ocean. And So that 14.7 pounds per square inch of atmospheric pressure is pretty average for us. But on top of a mountain, what do you think would happen?
When you're going, like, up a road on a mountain? Like
They
Mountain
do.
Mountain?
Yes. I like Mountain Mountain. And yes, when you go up, your ears pop. Because there's a pressure change. So do you think when you go up the mountain, does the atmospheric pressure increase or decrease?
Increase.
I hear both answers. What do we think?
Decrease.
Atmospheric pressure decreases, so why? Matt.
Because there's less air. There's the same components, but it's less air, so there'd be less atmospheric pressure.
Okay. So, like, if this, let's say there's the edge of space, this does not draw to scale, although we're going to try that later. If you're here at sea level, and then you think, well, atmospheric pressure is the mass of the column of air exerting pressure down on me, right? If you go up on the mountain, how does the column of air on top of you change?
It's shorter.
Yeah, there's just literally less air on top of you pressing down on you, so atmospheric pressure is less. You're going to experience less pressure because that column of air is shorter. And also what happens as you go up the mountain, as you increase in altitude, do you see?
The amount of air decreases?
Right, literally the concentration of air also decreases. If you go up high enough, you'll notice. Like they say football teams have to train to play games in Colorado because it's so much higher than, and so there's literally less concentration of air, so you're breathing less oxygen. Your body has to adjust to that. You feel more tired. Even like Massanutten or where I grew up in West Virginia, like everybody gets there and suddenly feels tired for a day because it's just a different amount of air. We're breathing less oxygen and we feel tired. But then you adjust. So, atmospheric pressure can be measured in other units. So we've been talking about 14.7 pounds per square inch. I'm going to make my L differently because you can't actually tell that's an L. Okay, so 14.7 pounds per square inch. Is a pressure unit, but you can really use any pressure unit to talk about atmospheric pressure. So, anyone know any other ways that we can measure? Joseph?
Like the barometer using inches
Okay, inches of...
from the liquid in the barometer.
Okay, so you can measure in however many inches of whatever liquid's in your barometer. If you guys watch the videos on the link that I sent, you'll see the water barometer that's in... Not the Netherlands. It was made in the Netherlands.
Denmark.
I think it's in Denmark now. And, yeah, the water barometer is like, 33 feet high? Because that's the height of the column of water has to be to measure atmospheric pressure. You can measure in, a lot of times barometers will use mercury as the liquid because mercury is, I think, the only metal that's liquid at room temperature and is very, very dense compared to pretty much any other liquid. It's also not the safest thing to handle. When I was a kid, science teachers would just like let you play with mercury in your hand because it's so awesome. But now apparently that's not okay anymore. We're not allowed to do that. So, you know, sorry.
ATM was another one.
Atmospheres. And so we say at sea level about 1.0 atmospheres is 29.9. What is it, 776? My memory is, well, I'm
For the atmosphere?
For mercury, 760. It's not on my note sheet anywhere. 760 millimeters of mercury, or, what did you say, 29.9? Is it 9.4, or do you not have to know that?
It said 29.9.
29.9, and what's our unit?
No.
Is it inches?
Inches.
Inches of what? Is that mercury too?
Yes.
Okay. So 760 millimeters and 29.9 inches must be about the same. So that's just showing pressure, and we'll kind of look at what air pressure can do here in a minute. Okay, so we're good. That is essentially what you will kind of need to know about the atmosphere and air pressure in general. It says do lab sheet, part 1, 3, and then 2. So would you please pass these around, Ryan? I'll get my copies. And we'll think about atmospheric pressure. Actually, I'm going to get this going. Sorry. If you feel like you're asphyxiating, let me know, and we'll try to fan the doors or something. There's no windows, so. Oh, put on goggles. Please pass out goggles. Y'all here in the front first. Here, you two quick, and then I can get some.
We could die.
Alright.
We could lose our vision.
Good job.
Losing your vision is bad.
Yeah.
Okay. Good.
They're kind of.
Don't throw at the girls anymore. No throwing at the girls.
Well,
And then you might want to re-aim the camera because right now it's looking at a bag. Okay, so our objective today, the first thing you want to write, our objective today is to observe atmospheric pressure. So write to observe atmospheric pressure down for your objective here. To observe atmospheric pressure. So the first thing it asks, is atmospheric pressure strong enough to crush a soda can? So make a hypothesis. Do you think that column of air sitting on top of us all the way up to space is strong enough or not to crush a soda can? Do we have opinions?
Yeah.
Okay, Lily thinks yes. What else do we think? Anyone else? Okay, everyone's going for yes here. Oh,
So you already.
here's a glitch I didn't think about. It won't stay down. Okay, we'll hold it there until the steam gushes out at my hand, you know. Alright, so here's our procedure. The water is heated to boiling, and a small amount of boiling water is put into each soda can. Hopefully the cans will get hot and heat up the water inside of them. The cans are kept hot right side up in the boiling water. Ice was put into 2 bowls. I really think we can get by with 1 bowl of ice. I don't know why they use 2. Can't figure that out. 1 can is put into the water right side up, and 1 put into the water upside down. So let's think about what might happen to these cans. Maybe I'll just use this metal thing here. Okay. So, what will happen to the cans when I place them, and boiling water could pop up out of the pot a little bit, you guys in front. So, when the boiling water in the pot heats up the cans, it'll boil that tiny bit of water that I put into the cans. And what will that water do? It's a liquid right now. What will the water do? It'll become steam. Okay, so then when that water becomes steam, liquid water has a small amount of volume, right? And when it becomes steam, it'll take up much more space because gases take up a lot more space than liquids, right? So then it'll drive all the air out of there, and we'll just have steam filling up the volume of the cans. Both cans, they're the same, okay? So then, the first can I'm going to just take and put right side up into the ice bath. So then what will happen to the steam inside the can?
Will become liquid.
The steam will get cold again and become a liquid, right? And then, what will happen? Nothing. Why?
Cooled off, it's liquid again.
Okay.
Oh, because the pressure.
Because the pressure will decrease, but that opening will be pointing upward because it's right side up, so air can just rush in, and the can won't be crushed because it'll just become full of air again. But the other can, I'm going to flip over and put opening side down into the ice bath. So air won't be able to get in. That can will also get cold from the ice. The steam inside will condense back into liquid, but will anything be able to fill up the can? No. So what will happen to the can? Chris? It'll crush. So what crushes the can?
Since there's nothing inside of the can, there's nothing to
Push out against the wall.
push out against the.
So what's
actual
pushing
pressure.
in on the wall of the can? Whoa. Not it. Awesome.
Where'd the other can go?
Yeah, that's the problem. That's a problem. No, you're not falling down too. Thank you.
Pencil catching on fire.
Oh.
Okay, so I know which can's going to be the right side up can. Alright, we have to wait until, like, steam is gooshing out.
Oh no.
No, Mrs. Matthias,
Yes.
wouldn't the water come up inside the can?
It does a little bit.
Upside down?
It does a little bit, and we'll see that more clearly with the clear jar that won't crush in a second.
It wouldn't,
But it won't fill the can enough to exert pressure outward. So there'll be not much inside the can to push out against the walls of the can. What will be pushing in to crush the can?
atmosphere pressure.
Right, that column of air that goes all the way up to space and surrounds the can. So hopefully it's getting really hot here. And I'm going to do the first can and then hopefully the second can. I'm going to do the first one with my bare hands and maybe get them cold first. You know. Alright, so the first one we expect nothing to happen, and we're going to write our data about the first can. So it says right side up can. That's what's happening right now. Nothing. Air rushed in. Nothing happened. There we go. Hooray. Now, I really want to not knock the whole pot of boiling water over anywhere at all. Everyone
The
is
second
backing up.
time.
Look at you guys.
This is
My brother did this one.
Alright, I hope it works. I don't see gushing steam, but I don't want to burn this thing any longer than I have to either, so. I'm not real coordinated. Okay, so our can definitely crushed pretty successfully because atmospheric pressure pushed in and there was nothing left to push out. So, write your observations. A right side up can, nothing happened. Upside down can, no air could fill it, so it just crushed inward. And you can make some notes in your observations about whatever you saw. Sources of error. Actually, the right side up can that fell over doesn't really have any water in it. The water was shallow enough that it didn't fill it up or anything, so it's not too bad. I don't think we had super error like I was worried about there. Okay. So make your notes, your observations. Oh, and some water did rush in, just like Max said it would. You can see it gushing out now. So, our discussion. And you can, let me see if I'm going to do anything. I'm going to light a candle, so keep your goggles on just in case. Because if this jar should ever crack, it would really be an unpleasant glass shooting across the room experience. Hopefully it won't, but that's why we wear the goggles. So the discussion. When the cans were heated, liquid water inside them turned into a
Yes.
gas. So the first one is gas. Okay. Ryan, when the cans were cooled, the gas did what?
The gas. Evaporated? No, it's water.
It's the opposite of evaporating. What's the opposite of evaporating?
Isn't that like condensation or something?
It condensed, yeah. So the gas condensed back into a liquid, yes. All right, when the cans were cooled, the gas condensed back into a liquid. Joseph, this made the pressure in both cans. So if they were full of gas and then the gas condensed to a liquid, the pressure did what? Go up or go down?
It went down.
Yes, goes down. So the pressure in both cans went down or decreased. and max. Atmospheric pressure comes from what? What causes it?
The column of air.
A column of air. So a column of air. Atmospheric pressure comes from a column of air that has a very large anyone, shout it out. Take a guess. It's okay to be wrong.
What do you mean very large?
The column of air has a very large, and then there's a blank. A very large
Pressure.
pressure or weight, mass. Yeah. And max, it extends from ground level up to space. So that whole column of air. And we'll define space a little better next week, maybe. Or maybe this week. We'll see how far we get. I get extra time with you guys today because I don't want you, like, running around during the service. So, let's see. Next one will be Duchesne. What happened to the right side up can to keep it from being crushed?
The air took the place of the gas.
Right, so it was right side up, so air was able to flow into the can and fill that space that was vacated when the gas turned into a liquid. So air rushed in or something like that. And Jessie, why didn't this happen to the upside down can? Why couldn't air get into the upside down can?
There was no opening for the air to enter into.
Okay, the opening was under the water, so air couldn't get in. So, no opening for the air to get in, or something like that. Alright, for the upside down can, the pressure inside the can was higher or lower? Jessie, was it higher or lower than the atmospheric pressure? So when I flipped that can over, the pressure inside the can was what than the pressure outside the can? Lower. Yep. The pressure inside the can was lower than the atmospheric pressure. And Meredith. Atmospheric pressure was greater than the strength of the walls of the can, so the can crushed, crumpled, squished in, whatever you like. Okay. So, I think we're going to skip down to part 3. So if you get that done and flip your page over. And you
Wait,
look at
what was
part
the,
3. Oh, go ahead.
I wasn't paying
Here.
attention.
Lower than atmospheric pressure.
Lower than.
The pressure inside the can that was upside down was lower than atmospheric pressure. And then the
Pressure
can
was
crushed in or crumpled. Okay. So look down there at the very bottom where it says Part 3 temperature. And I'm going to attempt here to make a bubble, which sometimes is more challenging than one might hope. I need a beaker. I have 2 beakers. Can't find any beakers. Awesome. Oh, here's one. Okay. So, attempting to make a bubble. Making a mess. I'm glad there's a sink in my room today. Okay.
Put your safety goggles on.
Starting with this. Okay.
That's a fancy tool.
I know, right? We take what we can get.
Just for mixing.
Okay, so I have a bubble now covering the top of this. This is an Erlenmeyer flask. Erlenmeyer flask, right here. Okay, so my bubble is covering the top. I promise, there's really one. It's hard to see. Can air get into or out of the flask when the bubble is covering the top? It can't get in, can't get out. So the amount of air in the flask is what it is, right? So, when I heat this up, see if you can, did I pop the bubble? I think bubble. That might happen a couple of times. When I heat up the air in the flask, none can get in and none can get out, but what will happen is the air gets hotter. Can you all see it?
Right.
So the bubble is getting bigger. It'll probably pop if I let it get too big. So you can see the air in the flask got hot and the bubble got bigger.
Up the top.
And I'll try to get some cooler air in the flask.
Everybody say hi.
Okay.
Me
So,
too.
I'll do it again. The air in the flask gets hot, but the amount of air can't change. It just gets hot. So what causes the bubble to expand if no more gas is entering the flask? Chris.
The air inside it gets hot and then it rises. Right?
Kind of.
Oh, it went down when you put it in.
Yep, because the air got cold, so it shrinks down. So yes, we're changing the volume of the air as it gets hot and gets cold because the bubble is sort of going up and down, but we're not changing the amount of air. So think of what happens to air molecules when they get hot. What do? Joseph?
They move faster.
They move faster. So if you are, let's say, I'm going to slide this. Yeah, put your hand down. So if I slide this at you and it hits you like that, and then it slides towards you and it hits you like tiniest bit, which one is going to hit you with more force? If I just slide it the tiniest bit, or if I really push it hard?
You really for sure.
Okay, so if things that are moving faster have more force, then why does the bubble get bigger? The hot air molecules.
Because there's more force pushing against the bubble.
Right. It's not that the amount of air changes, it's just that every air molecule gets more energy as it gets hotter, and it crashes into the bubble harder because it has more energy when it's hot. Hot molecules have more energy. Then when I cool off those air molecules, there's not more of them, there's not less of them, but they have less energy so they don't crash into the bubble as hard.
It's
So,
going down.
right. So you could just do that endlessly. It happens in my shower. I have this soap with this tiny little thing, and as the air in the shower gets hotter, if it's covered, like the bubble expands every time I take a shower. As the air gets hotter, it heats up the air inside the bottle, and I get this weird bubble. So, anyhow, that is part 3 temperature. Let's go over that. And it says, where am I? Okay, ladies, now I'm caught. One of you, are you Elise? You're Ava. Ava and Elise. Which one of you is older? You are. Okay. So, Ava. So sorry. Ava, when a bubble gets heated, what does it do? It expands. And when it gets cooled, it...
Shrinks.
Okay, shrinks, contracts. And Elise. Air molecules move how when they're heated? Faster, slower? Faster. When air molecules get heated, they move faster. So then they crash into the bubble.
And it pops.
Hopefully not. That was not the goal. Harder, softer, with less force, more force.
More force?
More force, harder, anything like that. So air molecules move faster when heated, so they hit the bubble harder. Even though no air can get in or out of the bubble does what, Bethany, when it's heated up? It gets bigger, expands, rises up. Bubble expands or rises up when the molecules hit it harder. Okay, so that's part 3. Any questions? Okay. So now I'm going to move hot stuff, cold stuff. I don't need any hot or cold water anymore, so I can just scoot all this away. Everybody can see better then. Right. We all know that's not a good idea right there. Oh dear. Okay. So we're on part 2. And we're going to have the same objective. I mean, it's just really we're just all observing atmospheric pressure today. I have soap on my hands, it's driving me crazy. So our hypothesis, is atmospheric pressure strong enough to move water? Like we already talked about how water is denser, it exerts more pressure than air, but can that giant column of air all the way up to space exert enough pressure to move water? What do we think? Duchesne says yes. Lily says yes. Okay, so yes or no, you pick. It's okay to be wrong on your hypothesis, so don't worry. I listed your materials. So we're going to write a procedure as I go. So, first procedure, I'll do it, and you tell me what you should write. Well, I already did the first step.
The candle was placed.
Right. The candle is placed in the pie pan. The candle was placed in the pie pan, or anything like that. We'll go with red, I think. We'll just keep stirring with this. How are you guys?
Nothing urgent.
Okay. Music. Go ahead. Okay. Red water. And I'm going to light our candle. So I would suggest adding, ouch. Okay. So I would make that first step. The candle was placed in the pie pan and lit. Just because I only gave you 3 choices, so just add and lit. Oh, why do I have trouble with candles? And then the pie pan was filled with colored water. Maybe would be the next step. I should have asked somebody that. The candle was placed in the pie pan and lit, and then the pan was filled with colored water. Well, not filled. I mean, you can be more precise if you like. Maybe filled a third of the way full with colored water. Okay, so now here's what we're going to do. I'm going to take the jar, I'm going to place it over the candle down into the water. So we all saw this happen with no water. What happens when I put the jar over the candle?
Same thing.
What happened?
Okay.
What happened to the candle?
It went out.
Burned out.
It'll eventually go out. But while it's still burning, what will it do?
Just go.
Chris.
It will fill the jar with gas, carbon dioxide, carbon
Yes, carbon dioxide.
carbon dioxide, and then it'll push it out.
Okay.
Yeah.
So, but it's also using up the gas too, right? It's going to use up oxygen gas because burning uses oxygen. Is it really going to go out? Okay. I don't have a backup candle this week, so.
What's wrong with your candles?
It's not a good candle year for me somehow. Alright. I'm going to pour off his wax. And hopefully expose a little extra wick.
You could just melt the wax with the iron.
I could. Much better.
Good job, machine.
Okay. That's going to go way better now. Alright, so we'll do it, then we'll talk about it, we'll write our discussion together. but what we want to do is watch what happens to the water level in the jar compared to the water level in the pan. So they're equal right now. And everyone can, if you want to come up and try to observe, but try not to bump the table. Hopefully the color will allow us to see well enough. So right now, the candle is using up oxygen, but it's producing carbon dioxide and water. Both are gases. Once it uses up all its oxygen, it'll go out, which I think it just did. And if you want to come look, you can see, don't let it come about. You can see the water level in the jar, and maybe bring the camera over and let the camera see it too for Jenna. It's sort of hard to see, but the water level in the jar came up to like right there, and the water level in the pan is lower than that. Can you all see it?
If you look at the candle, you can see where the water is.
Oh, you're right. That's good. Here, yeah, get a film of the red water touching the white candle. That is how, what a happy coincidence that is. Okay, so now you can take off your goggles. And if whoever has the bag can pass it along, and everyone can stick their goggles into the white bag. Just pass it.
Just pass it around.
Okay. So what shall we write about our discussion? What has gone on here?
Candles lit and placed in the pie pan.
Okay, so
And
once our
then
procedure's over and we've got the lit candle covered with the jar, and